All right, today we're going to move on to section 3.2. We've been doing a lot of work with quadratics as a specific type of polynomial function. So now in section 3.2, we're going to talk about all polynomial functions in general. So our learning targets today: identify polynomial functions and their degree, identify the zeros of a polynomial and their multiplicity, and analyze the graph of a polynomial function. Okay, so this is not on your handout, so I would write this somewhere maybe on the top of the handout. So we have the definition of a polynomial function here, and this is a very mathematical looking definition, but if you break it down a little bit, it's not as complicated as it may seem. So go ahead and write this down. First, a polynomial function is a function of the form f of x equals a sub n times x to the nth power plus a sub n minus 1 times x to the n minus 1th power, all the way down to a sub 1 times x plus a sub 0. So really what that's saying is a polynomial, we're talking about all polynomials in general. So that plus dot 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 in the middle is saying we can have as many terms in a polynomial function as we want. There is really no limit to how many terms we can have. So that's just what that represents there. Okay, and a sub n just means that's going to be the nth term in the polynomial. So to break it down, we're saying that where a sub n minus 1, all the way through a sub 1, a sub 0, those are real numbers, and n is a non-negative integer. The domain consists of all real numbers. So we're just saying that we have this polynomial, and you guys all have seen polynomial functions before, so this is not anything that's new. So we're saying that this statement here is saying that the coefficients, all of them are real numbers. So we're not going to have any imaginary numbers in a polynomial. Okay, so the coefficients, so all of the numbers that are within each term, they all have to be real numbers. Here we say that n is a non-negative integer. So n, in other words, are exponents. So here, so n minus 1, all of these exponents are positive integers. In other words, they are whole numbers. So in a polynomial, we're not going to have negative exponents, we're not going to have fractional exponents. Then it's not going to be considered a polynomial. And lastly, okay, you guys all know what this means. The domain consists of all real numbers. So for any polynomial on the graph, our domain is always going to go from negative infinity to infinity. So for any polynomial, so if it meets all of these, if the coefficients are real numbers, all the exponents are positive integers, then we know that the domain is going to be all real numbers. The last thing that you need to make note of is that the degree of the function is the largest power of x. So for example, we have been working with quadratic functions the last week or so. The highest degree was 2, so that was a second degree polynomial. So we always say that it's a third degree polynomial or a fourth degree polynomial based on the highest degree in the equation. Okay, the highest power of x. That is, you want to make note of that. That is when it's in standard form. So when the function is in standard form, then that highest power that you see is the degree of that polynomial. So let's look at a couple of different equations and determine which ones are polynomial functions and which ones are not. If they are a polynomial, then we want to state the degree. So right here we have 3 minus 2x to the 5th. So we have to go through our 3 criteria to make sure that this is a polynomial. 1, are the coefficients real numbers? So yes, we have 3 and -2. Those are real numbers. 2, are our exponents whole numbers, positive whole numbers? So yes, the exponents we have here are 0 and 5. So those both are positive whole numbers. So we would say yes, this is a polynomial. And the degree, remember when it's in standard form, this is not really in standard form. We can rewrite this -2x to the 5th plus 3. So our highest exponent, our highest power in this equation is 5. So our degree is 5. Okay, the next one we have g of x is equal to the square root of x plus 5. So we go through our criteria. 1, are the coefficients real numbers? So we have a coefficient of 1 and a coefficient of 5. So yes, we have real number coefficients. Are the exponents integers? Are the exponents positive and whole numbers? So that one, if you can remember back to Algebra 2, the square root of x, how can that be rewritten using an exponent? So remember, taking the square root is the same thing as raising a number to the half power. So this is the same thing as x to the half plus 5. So if you see a square root or a cube root or any sort of root like that, that means you're raising it to a fractional exponent. So you would say no, this is not a polynomial because we have a fraction as an exponent. Next we have h of x is equal to -3x cubed times x plus 2 squared. So do we have real number coefficients? Yes, everything in here is a real number. There's no imaginary numbers. Are the exponents positive whole numbers? Yes, we only have exponents of 3 and 2. So we would say yes. But the tricky thing here is what is the degree, because this is not in standard form. So you cannot say that the degree is 3. You have to think about how would you take this function and get it into standard form. What would you have to do? So to get this into standard form, you would take your x plus 2 squared, you would multiply that out, distribute your -3x cubed, and then combine like terms. So we know we're going to be multiplying all this stuff together. So we're going to be multiplying an x squared term times an x cubed term. What do we do with exponents when we multiply like bases? We add their exponents. So since I'm multiplying an x cubed term times an x squared term, I take 3 plus 2, which is 5. So I know if I were to multiply this out and put it into standard form, I would get a degree of 5. So when your equation is not in standard form, add the exponents together, and that's going to be your degree. So you don't actually have to multiply it all out. You just know when you multiply it out, your highest degree will be 5. All right, so f of x is equal to 3x to the 5th over 5 minus 2x. Go through our criteria. 1, do we have real number coefficients? Yes. 3, 5, and -2. Those are all real numbers. Are the exponents positive integers? Yes. Everything's positive, everything's an integer. Okay, we don't have any decimal or fraction exponents. Is the domain all real numbers? No. Okay, we have a restriction on the domain. Remember, when there is a fraction, when our function is a fraction, the domain or the denominator cannot be equal to 0. So in this case, 5 minus 2x cannot be equal to 0, which means x cannot be equal to 5 halves. So the domain is not all real numbers. It does not include 5 halves as a part of the domain. So no, this is not a polynomial. Last one, g of x is equal to 6. Questions, real number coefficients? Yes, 6 is our only coefficient and it's real. Do we have positive integer exponents? Yes. The exponent in this function is x to the 0. Okay, because x to the 0 is 1, so we don't technically write it in there, but that's what the exponent is going to be. And the domain is all real numbers. So yes, this is a polynomial, and the degree is 0. Okay, because that g of x equals to 6, that's just going to be a straight line at y equals 6 all the way across. So it's just a different type of polynomial. All right, what I want you to do is to go ahead and pause the video and try to look at each one of these functions and determine, is it a function or not? And if it is a function, then tell me the degree. So pause the video and go ahead and figure that out for yourself. Pause or restart the video when everybody is ready. All right, so you should have answers now to each one of these problems. So I'm just going to go through the answers to them really quick, just so you know if you got them right or not. So the first one is yes, with a degree of 3. It follows all the criteria. The second one is yes, with a degree of 7. This one's not in standard form, so you'd add your exponents together. So we have an exponent of 1, an exponent of 4, and an exponent of 2. So a degree of 7. H of x, that would be yes. It follows all of our criteria. The degree is equal to 3. F of x, nope, because we have negative exponents. And lastly, the last one is also no, because e is not an integer. It is a decimal, and we can't, in polynomials, we don't have decimal exponents. All right, let's talk about what a power function is. So a power function is of the form f of x is equal to x to the nth power. And n can be any positive integer. Okay, so if we want to have the because it represents a polynomial, so the exponent needs to be a positive integer. So what we know about power functions, if n is odd, so for example, if I have x to the first power, or x to the third power, x to the fifth power, so if n, that exponent, is an odd number, then our polynomial is going to start and finish in opposite directions. So what that means is, so x to the first, that is a line, that is a linear equation. So a line starts low and ends high. Same thing with x cubed. That is also an odd function. If you graph an x cubed, which we have in before, it starts low here and it curves up and ends high. So it starts down negative infinity up to positive infinity. X to the fifth does the same thing. Okay, it's just going to have a little bit different of a shape, but it always starts low and ends high. So if it's odd, your end behavior is opposite. One's going to be high, one's going to be low. On the other hand, if n is even, so for example, if we have x squared, x to the fourth, x to the sixth, and so on, that means our graph is going to start and end in the same direction. So for example, when I have x squared, that is a parabola. So that starts high and ends high. So they start and end in the same direction. X to the fourth does the same thing. It starts high, kind of does a little something in the middle, and then it ends high. So if n is even, the graph will always start and end in the same direction. So we're using this information to just be able to analyze the graphs a little bit. You should be able to look at a polynomial function and have a good idea of what the graph should look like, so that when we graph it and we use those graphs to analyze, you know if you're on the right track, if you're using those graphs in the correct way. Okay, so the end behavior of any polynomial function can be related to the power function of the same degree. So any polynomial function, if you have a polynomial function that's a 6th degree polynomial, that means the degree is even. So it will have the same end behavior of x to the 6th. Okay? If you have a polynomial function that is an odd degree, so a polynomial function that has a degree of 3, then it will have the same end behavior as x cubed. Okay? So that degree tells you what the end behavior is going to be. All right, so let's look at this polynomial function. I want you to tell me the degree of it, the end behavior, the zeros, and the multiplicity. So we're going to talk about what that means with the multiplicity. The zeros, remember, when we're talking about zeros, we're talking about the x-intercepts, because we're talking about when y is equal to 0. Okay, so let's just start at the beginning. What is the degree of this polynomial? So first ask yourself, is this polynomial in standard form? It is not, so then we have to think about, okay, to get this into standard form, we'd have to multiply everything out. So we're multiplying a 2nd degree, a 1st degree, and a 3rd degree, okay, of x to the 2nd, x to the 1st, and x to the 3rd. We're multiplying all those together. When we multiply like bases, we add. So the degree of this polynomial is going to be 2 plus 1 plus 3, which is 6. So that tells us what our end behavior is going to look like. Now listen carefully, because this is what I'm going to be expecting from you when I ask for the end behavior. The first thing I want you to tell me is what is the power function that it has the same end behavior as. So since this is a 6th degree polynomial, the end behavior is going to be the same as f of x is equal to x to the 6th. So first tell me what power function has the same end behavior as this polynomial. So x to the 6th. Then I want you to describe it to me in words. So it is going to rise to the left and fall to the right. Okay. So on the left, so since this is a positive polynomial function, it's going up in both ways. So rising to the left and, sorry, it's even. So it's the same direction. So rise to the left and rise to the right. Sorry about that. Since it's even, it's going to be the same direction. So you can always check that on your calculator. So if I were to put in y is equal to x to the 6th, I'm just going to graph zoom 6 in my normal. You can see that that's what the graph of x to the 6th looks like. On the left side, okay, it's going to rise up to the left and it's going to rise up to the right. So the end behavior, what is it doing on the left? What is it doing on the right? Okay. So that's what I want you to describe it to me in words. All right, so the end behavior, it rises to the left, rises to the right. Now the zeros, those are our x-intercepts. So we're setting y equal to 0. So x squared times x minus 3 times x plus 2 cubed. So here we already have it in factored form. We know that we have x squared times x minus 3 times x plus 2 cubed. All of that is equal to 0. So when I have two or more things multiplied together and equal to 0, I know that one or all of them has to be equal to 0. Okay. So x squared is equal to 0. So my intercept, my 0, x is equal to 0 is 1, 0, or 1 x-intercept. X is equal to 3 is my other x-intercept, or 0. And x is equal to negative 2. Okay. So that is where we know it's going to cross the x-axis when y is equal to 0. All right, the multiplicity. If a 0 has an odd multiplicity, the function crosses at that 0. If a 0 has an even multiplicity, the function touches at that 0. So multiplicity means that is how many times that 0 occurs in the function. So for my x is equal to 0, since this came from an x squared, that means that 0 occurs twice in my function. It has an even multiplicity. So it touches the graph at 0. My x minus 3, okay, that was an odd multiplicity. They had a degree of 1. So x minus 3 had a degree of 1, so that's an odd multiplicity. So that means it crosses the x-axis at 3. And my x plus 2, 0, that had a degree of 3. So that was also an odd multiplicity, which means my graph crosses at that 0. So what that looks like when we graph it. Okay, so we know that we have an x-intercept of 0, we have an x-intercept of 3, and an x-intercept of negative 2. So our end behavior tells us that it's rising to the left and rising to the right. So over here, my graph is starting up. It's going to rise to the left over here. Since my x equals negative 2 intercept has an odd multiplicity, it comes down and crosses the x-axis at negative 2. My x equals 0 had an even multiplicity, which means it's just going to touch the x-axis at 0. So it's going to touch it and come back off. So it kind of bounces off of there. It doesn't go all the way through, it just bounces off. And somewhere it's going to come back up and cross at x equals 3. So the end behavior kind of gives you an idea of if you're doing it right with the touches and the crosses, because you want to make sure that if, since it was x to the 6th, it would rise to the left and rise to the right. So the end behavior needs to be the same on both sides. So crosses through negative 2, touches or bounces off at 0, and crosses through the x equals 3. Okay, and again, if you want to check that on your calculator, you can. So we have x squared. Oops. Let's go ahead and clear all that. X squared times x minus 3 times x plus 2 cubed. Graph that. You can see it go through, touch, and then go back through. All right. Okay, let's do another one. So we have this polynomial here. We have f of x equals negative x cubed times x plus 2 to the 4th times x minus 8. All right, so first thing we're going to look for is what is the degree. So again, this is not in standard form. So if we were to multiply this all out, we're multiplying an x to the third, an x to the fourth, and an x to the first. So 3 plus 4 plus 1 is 8. So we have a degree of 8. The end behavior is a little bit different on this one. So since I have a degree of 8, the power function is going to be x to the 8th. However, the end behavior is going to be a little bit different because we have this negative out here. So you have to pay attention to whether your first coefficient is a positive or a negative, because this is actually going to have the end behavior of negative x to the 8th. So what does a negative do to a graph? It flips the graph over the x-axis. So since there's that negative out there, the end behavior gets flipped upside down. So it's still even, so it still has to have the same end behavior on both sides. However, now it flips over the x-axis. So it's going to fall to the left, and it's going to fall to the right. So it's even degree, so the end behavior has to be the same on both sides. But since it gets reflected over the x-axis, it's going to be going down on both sides. All right, so then our zeros are x-intercepts. So we're setting our equation equal to 0 and solving for x. So we have negative x to the third times x plus 2 to the fourth times x minus 8. So all three things being multiplied together to equal 0. So I'm going to set each one equal to 0. So my first 0 is x equals 0. My second, x plus 2 equals 0, so I have x equals negative 2, and x equals 8. So let's talk about the multiplicity of each. This first one, negative x cubed, had a multiplicity of 3. So a multiplicity of 3, an odd multiplicity, which means it crosses through the x-axis. X plus 2, so x equals negative 2s are 0, and that had a even multiplicity, which means it's occurring an even number of times in our function. Okay, because we have x plus 2 times x plus 2 times x plus 2 times x plus 2. So that negative 2 occurs 4 times in our function. So the multiplicity is 4. It's an even multiplicity, which means it's going to just touch the x-axis and bounce right off. Okay. X minus 8, that was just raised to the first power, so it only occurs once in our function. So the 0 x equals 8 only occurs once in the function, so it has a multiplicity of 1, which is an odd multiplicity, so it's going to cross through the x-axis. Okay. So again, what that's going to look like is we have zeros at 0, negative 2, and 8. So we know our end behavior tells us it's falling to the left and falling to the right. So it's going to start down here on the left because we know it's going to fall down there. The x equals negative 2 is a even multiplicity, so it's going to touch and bounce back down. Go up towards the x equals 0. It's going to do something there in the middle we're not sure of, but that's okay. So we x equals 0 had an odd multiplicity, so it crosses through, comes back down. My x equals 8 had an odd multiplicity, so it also crosses through and falls to the right. So again, let's take a look at that on the calculator. Make sure that we did that right. So negative x cubed times x plus 2 to the 4th times x minus 8. Graph that. And we got that right. So it goes up pretty high up there, but then it comes right back down. So touches at -2, crosses through 0, goes way up high, comes back down and crosses through -8. All right, let's go the other way around. So given this polynomial equation, okay, we have zeros here. See if we can take the zeros, and they all have a multiplicity of 1, and write our function. So we know that our 0, if we have a 0 of 0, that means that we just had an x to some power. Since it's a multiplicity of 1, just x to the first power. If our 0 is -4, that means in our function we had x plus 4 with a multiplicity of 1, so to the first power. If we had 0 of +2, that means we had x minus 2 in our function. Okay. If we have zeros of -3, which has a multiplicity of 2, and 5, which has a multiplicity of 1. So we'll write that function. So we have f of x. If our 0 is -3, that means in our function we had x plus 3, because that's what we set equal to 0 to solve. Has a multiplicity of 2, so we're going to square it. We also have a 0 of 5, so x minus 5 is what's in our function, and that had a multiplicity of 1. All right, go ahead and really quick see if you can do that third one on your own. All right, you should have gotten f of x is equal to x squared times x minus 6 cubed times x plus 2 to the 4th. All right, we're just going to take, the last thing we're going to do is just take everything we just learned and put it all together to graph our function. Oops. All right, okay, so the first thing we're going to do, find the degree and the end behavior of the polynomial. We're also going to find the x and y intercepts of the graph. Determine whether the graph crosses or touches at each x-intercept. And we'll graph it using a graphing utility to figure out if there's any local max or local min. Okay. Then, using all of that information, we can graph it. So once we know what the degree is, what the end behavior looks like, the x and y intercepts, and where it crosses, touches, that sort of thing, we can go ahead and graph it by hand using all that information. Okay, so I'm just going to go through this really quickly. So the degree and the end behavior. So our degree, we have 1 plus 2 plus 1 plus 2. So our degree is going to be, oops, I lost mine, 6. We also have, so our end behavior is going to be the same of f of x is equal to x to the 6. So the power function that's the same is x to the 6. And it's a positive, okay, our first coefficient is positive, so it's going to rise to the left and rise to the right. X and y intercepts. X-intercepts. So we have x is equal to 0, so 0, 0. And that was a multiplicity of 1, so that is going to cross the x-axis. x equals 4, so 4, 0, which has a multiplicity of 2. So that's going to touch the x-axis because that's an even multiplicity. X is equal to 3. That has a multiplicity of 1. So that's an odd multiplicity, so it's going to cross the x-axis. And x squared plus 1, you have to be careful with that because if you solve that, you're going to end up taking the square root of a negative. So that means there's no x-intercept for that particular piece of the function. Okay, so we just have 3 x-intercepts, one at 0, one at 4, and one at 3. Crosses at 0, touches at 4, crosses at 3. Our y-intercept, just plug in 0 for x. So we have 0 times negative 4 times 3 times 1. So our y-intercept is going to be 0, 0. Okay, so same steps for finding the y-intercepts as we always have. So determine whether the graph crosses and touches at each. We've done that. Okay, we looked at the multiplicity, odd multiplicity it crosses, even multiplicity it touches. So let's go ahead and graph this using our graphing calculator. So we have x times x minus 4 squared times x plus 3 times x squared plus 1. All right, so if we're trying to find the local max and the local min, it looks like we're going to have to change our window a little bit because it looks like it goes pretty high up on the y-axis. Still going up there pretty high. So there we go. Okay, so there we can see our local max. Let's change it to see if we have any local min. So negative 100 maybe? Oh, still goes pretty far down there. So we can do this one, negative 1,000 also. All right, there we go. So you got to change your window a little bit so you can see the max and the min. So in your calculator, you need to change your y min to negative 1,000, y max to 1,000. 500 might have worked also, but at least now we can see where the max and the min is. So second calc, find your local minimum. Okay, we get a minimum of negative 402 at x equals negative 2.3. So a minimum negative 402.18 at x is equal to negative 2.32. Okay. Then you need to find your local maximum. Okay, so again, I'm going through this pretty quickly because this is all stuff that we have done before. So use that prior knowledge. Local maximum we get is y is equal to 224.64, and that occurs at x is equal to 2.45. So go ahead and record both of those so you have that information. So we can use that information now to graph our quadratic function, or I'm sorry, our polynomial function. Okay. So use that information. We know that the end behavior, it was rising to the right and rising to the left. We know that our x-intercepts was 0, 0, 4, 0. And negative 3, 0. Okay, and it crosses at 0, 0, touches at 4, 0, and crosses at negative 3, 0. Let's go ahead and change this so we're counting by 100, since we know our maximum and minimum are pretty high up there. All right, so we know that the local minimum was about negative 2.3 and down to negative 402, so about there. Okay. Then we know our local maxima was 2.45 and positive 224, so about here. Starts high and ends high, crosses through negative 3, crosses through 0, touches at 4, and comes back up. Okay, so that's how you use that information to determine what your graph is going to look like. All right, so the last couple, the domain and the range, this is a polynomial function, so the domain is always going to be from negative infinity to infinity. And our range, the lowest point on our graph is at negative 402.18, and the highest point on our graph, both sides go up to infinity. So from negative 402.18 all the way up to infinity. Our graph is going to be decreasing from negative infinity to, so from negative infinity up to this point right here is when it stops decreasing. Okay, so that right there, we're looking at our x intervals, so that is at negative 2.32. It also decreases from this point to this point. So the x interval there is from 2.45 to 4. We also have some increasing parts. So from here to here, our graph is going to be increasing. So the x interval from that is going to be negative 2.32 up until 2.45. It also increases from here on. So from 4 to infinity. Okay, so that's just a matter of taking what we now can figure out about a polynomial function, so you can look at the function, figure out the degree, figure out where it's going to cross, where it's going to touch the x-axis, and then the end behavior of it using the degree. Use your calculator to find the local max and local min. Use all that information to graph it. Okay. So at this point, you have an assignment that you're going to be working on with your groups. So we have page 183, 39 through 43 odd, and 47 through 79 every other odd. You have the rest of the class period to work on it to get started, so you can talk to your groups, ask questions if you have them, kind of try and figure it out. Whatever you have left is going to be your homework due next class period.